In the middle of the Pacific Ocean, thousands of kilometers from any city, a vast pulse of warm water begins to move. At first, almost nothing seems unusual. But within months, rivers will flood, crops will fail, coral reefs will bleach, and weather patterns across the entire planet will begin to change. This phenomenon has shaped civilizations, disrupted economies, and influenced the lives of billions of people. Scientists call it El Niño. And the next great shift may already be beginning. This is the story of the ocean that helps control the world's weather. El Niño is not a storm. It is not a hurricane, a cyclone, or a single weather event. It is a periodic warming of the central and eastern tropical Pacific Ocean, caused by a complex interaction between the ocean and the atmosphere. Under normal conditions, trade winds blow from east to west across the Pacific, pushing warm surface water toward Indonesia and Australia. Cold, nutrient-rich water rises near South America. This balance helps shape rainfall across the tropics. But every few years, that balance weakens. Warm water spreads eastward.
Earth's trade winds blow across the tropical Pacific. They push warm surface water toward the west. This causes cold water to rise from the deep. This entire process is known as upwelling.
The atmosphere responds. And the effects can ripple across nearly every continent on Earth. The birth of El Niño begins with a change in the winds. When trade winds weaken, warm surface water is no longer held in the western Pacific. It begins to move eastward along the equator. This movement deepens the thermocline in the eastern Pacific and suppresses the upwelling of cold water. Sea surface temperatures rise. Warmer water heats the air above it. Clouds and thunderstorms shift eastward. This is not simply an ocean event. It is a coupled ocean-atmosphere feedback. First, clearly explained by meteorologist Jacob Bjerknes in the 1960s.
During El Niño, trade winds weaken. Warm water rushes east, causing the thermocline to sink. This cuts off the cold water from the surface.
Once the feedback strengthens, El Niño can grow into one of the most powerful natural climate disturbances on Earth. A change in the Pacific does not stay in the Pacific. El Niño alters the position of tropical rainfall, and that change affects atmospheric circulation around the world. Scientists call these connections teleconnections. In some regions, rainfall increases. In others, it decreases. Typical El Niño patterns include wetter conditions in parts of Peru and Ecuador, drier conditions in parts of Australia, Indonesia, and southern Africa, changes in the Indian monsoon, altered storm tracks in North and South America. Every El Niño is different.
During the strong El Niño of 2015 and 16, green areas saw much wetter conditions, while brown areas were drier.
But the message is the same. The atmosphere is connected. What happens above one ocean can influence weather thousands of kilometers away. For millions of people, El Niño is experienced not as a scientific pattern, but as disaster. Floods can destroy homes, roads, and farmland. Drought can reduce harvests, dry reservoirs, and increase wildfire risk. During major El Niño events, Indonesia has experienced severe drought and fires. Peru has suffered destructive flooding. Southern Africa has faced crop failures and water shortages. These impacts depend on local geography, infrastructure, and preparedness. El Niño does not determine a disaster by itself, but it can greatly increase the probability of extreme conditions. One of the first places humans noticed El Niño was the sea. Off the coast of Peru, cold upwelling normally brings nutrients to the surface, supporting one of the world's most productive fisheries. During El Niño, upwelling weakens. Nutrient supply falls. Plankton declines. Fish populations can shift or become less abundant. Seabirds and marine mammals may struggle to find food. The ocean's food web begins to change. This is a reminder that climate is not only about weather. It is also about ecosystems. El Niño can influence two of humanity's most essential resources, food and water. Reduced rainfall can lower soil moisture and crop yields. Reservoirs may decline. Groundwater use may increase. At the same time, floods can damage crops, roads, and storage facilities. Food prices are affected not only by climate, but by trade, energy costs, policy, and markets. Yet climate variability can be a critical trigger. For vulnerable communities, even modest increases in food prices or water stress can have serious consequences. Now comes the question scientists are still trying to answer. Is El Niño becoming stronger because of climate change? The evidence is clear that the planet is warming. The oceans are absorbing most of the excess heat. A warmer atmosphere can hold more moisture, increasing the potential for heavier rainfall. Higher temperatures can intensify drought impacts, but the scientific evidence is not yet sufficient to conclude with high confidence that El Niño itself has already become systematically stronger. This distinction is crucial. Stronger impacts do not necessarily mean a stronger El Niño. Research continues, and uncertainty is being measured, not ignored. What happens next? Scientists are now monitoring the Pacific with satellites, ocean buoys, Argo floats, and increasingly powerful climate models. Seasonal forecasts can often provide months of advance warning. The future challenge may not be a dramatically stronger El Niño. It may be a more sensitive world, a world with higher temperatures, greater water demand, more exposed infrastructure, and ecosystems already under stress. Forecasting is evolving from predicting ocean temperatures to predicting risks. Crop losses, floods, droughts, wildfire conditions, fisheries impacts. Knowledge is becoming a tool of resilience. For thousands of years, the Pacific has helped shape Earth's climate. It has influenced monsoons, rivers, fisheries, forests, coral reefs, and the harvests of civilizations long before modern science existed. El Niño is part of that ancient rhythm. What has changed is us. We have learned to measure the winds, map the currents, and watch the ocean from space. We have learned that the atmosphere above every country is connected, and that the future of food, water, ecosystems, and cities is tied to processes that begin far beyond the horizon. Science has not removed uncertainty, but it has transformed surprise into preparation, isolation into cooperation, and ignorance into understanding.